I began my plot by first converting the bearings from PSC to true. I did that by using TVMDC. And for the Saybrook breakwater light, I have a bearing of 300 degrees true, which is right here. And then for the Rocky Point Tower, we have a bearing of 234 degrees true. And then for the tank on Black Point, we have a bearing of 5 degrees true. And that gives us our 9 o'clock position right here, which is 41 degrees, 12.7 minutes north, and 72 degrees, 13.2 minutes west. I calculated my course to steer for number 2 by first measuring 1 nautical mile under the R8A buoy, and then I used a triangle to plot a course in line 1 nautical mile under the buoy, and that gave me a course of 268 degrees true. All right, number 5. For the this is for the running fix. First, I plotted my 913 right here and my 920, which is right here, this longer line going up, bearing to the Saybrook breakwaters. And then I multiplied the difference of time, which would be 7 minutes, by the speed, and then divided by 60 to get 1.45 nautical miles. I then moved my 913 fix over 1.45 nautical miles, which is right here. And where that intercepts with the 920 fix is my running fix. And that location is 41 degrees, 13.1 minutes north, and 72 degrees, 18.7 minutes west. For number 7, which is position at 934, yeah, Cornfield. Oh, yes. From Cornfield Point, I traced an arc with a distance of 3.8 nautical miles. Here we got my little markers up here. So Cornfield Point's up here. I used a compass to trace a 3.8 nautical mile arc. And then I used a bearing from Mulford Point of 116 degrees true at 5.4 nautical miles. And where they intercept gives me my 935 position, which is 41 degrees, 11.9 minutes north, 72 degrees, 23.4 minutes west. Alrighty, who's next? Number 12, oh boy. Alright. So for number 12, first I calculated my computed visibility, starting by converting the feet of the height of the eye and the height of the light. The Horton Point light, I converted them from feet to nautical miles. And then I added them, and that gave me my geographic range of 17 nautical miles. I then used the visibility and the nominal range provided by the book, and I used the graph in the green book to get a luminous range of 8 nautical miles. I then, like the problem before, from Horton Point, where is it? Right here. Where is it? Yeah, Horton Point. I drew here we go. An 8-mile arc from Horton Point right here, which is right here. You can see. Using the interception point at right there. The interception point of my 1020 track line with the arc is where we will lose sight of the Horton Point light. I then measured the distance between the interception point and my 1020 position. And then that gave me 2.3 nautical miles. And I divided that by the speed, which was 12 knots. And then I multiplied that by 60, which gave me a time of 11 minutes. And then 11.5 minutes. And then 11.5 plus 1020 would give us a time of 10:31.5, rounding up to 10:32. Alrighty. Set and drift. Alright. Okay. I started this by first plotting a 30-minute DR along my 1020 track line. Using a triangle, I measured the angle right here, 1050 position, and that gave me a direction or a set of 358 degrees true. For the drift, I measured the distance from the DR to the 1050 point, which is this little dotted line right here. And then using a compass, I got a measurement of 0.6 nautical miles. And I divided that by the difference in time, which is 30 minutes. And then I multiplied that by 60 to get a speed or drift of 1.2 knots. And here we go, there's the equation. And number 18. For question 18, I used the gyro error of the 3 degrees east, which was provided in number 1. There we go. And then I added that to the 336 per gyro compass, and I got a true direction of 339 degrees true.